Hello students, today we are in lecture number 14 of chapter 1 of the same section, electrostatics. The students, today we will solve few questions of electric flux and then we will move in last of the lecture for the statement of Gauss Law. I am B.S. Pandey. A student, suppose we have been asked to find this is your example today, first example, to find the electric flux by the individual phases of this cube. This is a cube, three-dimensional body immersed in uniform electric field. Here this E is EI along the x-axis. Here we can draw the specific axis x, y, z. If the electric field is in this particular direction, A is the side of cube. You have to find the electric flux through each phases. If you want, you can write the name of vertices A, B, C, D, E, F, G and then H, so that you will be comfortable to represent the phases. Now you have to find the flux through each phases individually, and then you have to find the net flux by this body, this cubical body. In last lecture we have studied if any closed body completely immersed into uniform electric field, then the total flux will be 0. Remember, here we are going to find out the flux through each phases. Here the first one, the flux by this phase A, B, C, G. A, B, C, G. Okay, A, B, C, G. What is the formula, students? Actually, the formula is E dot A. This is the electric field and this is the area vector. Area vector, I would like to recall you about the area vector, although you have been studied in standard 11th about the area vector. This is area vector. This must be perpendicular. Must be perpendicular to the surface area. Okay, surface area. You have been studying already the surface area. For example, if I'm asking the area vector of this board on which we are studying, the direction of area vector, the area vector of this particular slab, you can write the area of this slab, that is the length into breadth. But what will be this is the magnitude, but what will be the direction of this area? So the direction will be perpendicular. Okay, perpendicular upward. I will ask the direction of area vector of this slab in this way, what is the area vector? Then area will be this one and the area vector will be in the direction of this one, that is the perpendicular to the surface. So this will be the direction of area vector here. So the area vector, okay, area of this side A, B, C, Z, that is the A, B, C, Z. Of course, this is this direction, okay, in this direction, and this is minus I cap. And what will be the area, student? So area will be, since this is the square plate, it is the cube, this is the square plate, the area will be A square. Here the side is A, so the A square. So you can write here the in vector EI dot A square, and the direction is minus I cap of this area. It is minus I cap. So the flux is minus E A square. Here the I dot I will be 1. In similar way, you will find the flux through this phase ABHF. ABHF. It is E dot A again. So the directly I'm writing here the E I cap. For each phase the electric field will be same because the electric field is going in X direction. So the EI, now the area ABHF. Here the area is, magnitude is A square, and the direction will be along the Z direction because this is the area will be upward and this is the Z direction. So K cap. Okay, it is the K cap. And what will be the answer? I dot K will be 0. Try to recall, students, in last class we have been studied if the area vector is perpendicular to the electric field, the flux will be 0. And it is quite obvious if you will try to just use your IQ, if this plate is this one, and the electric field lines is going in this way, so this thin surface will not able to stop or not able to count the field line. That's why the flux will be 0. Okay, now in same way you can find the flux through each phases. Directly I'm writing which phase will give you the flux 0 and which will give you the flux as the quantity. Okay, so I hope you are well aware. You can find out this phase FHDE, phi FHDE. FHDE will give you the flux and it is EI dot A square. Area will be I cap. Area will be I cap. So we can write here it is E A square. Okay. Now for other phases, if you'll find the phi CBHD, you will find the flux 0. And this is also equal the flux by CDEG. Try to see the diagram CDEG, and this one will not stop or count any field lines. In similar way, the number of phases, total the 6 phases are there. CDHB, in similar way AGEF, phi AGEF, 1 2 3 here 4 5 and 6, the total phases we have been counted here. And the total flux, if you will find, this is the flux by individual phases. Okay, this is nothing but the for the practice. Further you will get help from this calculation, from this practice. Now the total flux, student, the total flux through this cube phi net will be how much? Here you can find out the 0 for everywhere except this one and this one, and adding these two, since it is minus and plus, you will get again minus EA square plus EA square, and it is 0. So the net flux will be 0. As we have been written in note point, any closed body completely immersed into uniform electric field give you 0 counting of flux. That is, the total flux will be how much? 0. Okay, now the next example, student, I'm giving you this particular example has been asked several times in your board examination. Try to solve by yourself. This is your classwork, student. You have to find the flux by this cylindrical body. This is the cylindrical body, and it is immersed into uniform electric field. Here E is the uniform electric field along x-axis, uniform. Okay, Now the radius of the cylinder is A and length is L. The cylinder having the length L and R is the radius. You have to find, and this is the cylinder. You have to find the flux through or by cylinder. This is your question. Okay, try to solve this question. Pause the video and try to solve the question. Okay, now the answer, student. Here we are having total 3 surface area. 1, the cylinder plane surface. This is the area minus I cap. 2, it is area same as this one, same as this area. It is I cap. And the third is this curve one. Now what will be the direction of curve one? Actually, student, we can take the direction of curve one as the Z also, as the Y also. But here, since the curved surface is not only along the Y or Z, actually it is along all the directions. So our standard direction we are using here the R cap, because radial vector will be everywhere. So this is R cap. And the important thing, this R cap will be perpendicular everywhere to the I or minus I. It will be perpendicular to the I cap. Remember, this will be the perpendicular to the I cap. I cap, this is the direction of electric field, and this R cap, this is the direction of area vector of which surface? Curved surface of the cylinder. Overall, we are having only 3 surfaces, and we can write here the total net flux phi net here, phi 1, phi 2 and phi 3. Phi 1, okay, this is the surface, plus phi 2, okay, this is the surface, and phi 3, this is the curve, phi curve surface. Now we are going to write the net flux. Here for this surface it is EI dot area, it is A, which is pi r square. You can write pi r square and minus I cap, plus for the second EI again pi r square and direction I cap, plus EI dot the curved surface area of cylinder, it is 2 pi RL and the direction is R cap. Here I dot minus I, it will be the minus, and E pi r square, here plus E pi r square, a plus this I dot R, since both are perpendicular, so it will be 0, and totally we are having this is equals to this one cancel out, and again we are having the net flux 0. The question will be asked in 2 ways. One that has been asked, and the second, it may be to prove that, student, the question is coming, prove that a cylindrical body completely immersed in uniform electric field will give you the net flux 0. And for 2 or 3 marks you will be asked in your board examination. Okay. Now the next question for practice, student. Let us take a question from NCRT. Okay, and this question has been asked in competition also. This is classwork. If you can solve, I will give you some time. Again, this is the cubical body, and this cubical body is being placed in uniform electric field, but this electric field is changing. Okay, student, this is the cubical body, this is the Z axis, sorry, okay, this cubical body is placed on x-axis, but from certain distance from the origin, and this is the origin, this is the z, x and y, and this is the cube of side A, and it is placed at a distance. Here this is A from origin. This vertex is a distance away. Okay, and the electric field it is given. This is NCERT question, remember student. E is given E naught x I. Okay, this is the electric field. You have been given E naught x. It might be the E naught x square or anything else. You can have the x plus y also. Okay, don't worry. If this is the question, then you will be capable. You will be able to solve this question. I'm giving you the concept. This is the electric field. A is the side of Q. Now you have to find the net electric flux. Find net flux by Q. Okay, and this is the electric field. But this electric field, remember, is not uniform. It is not constant. As you are moving, for every x meter, the electric field is changing. For example, if x is 0, that is at origin, electric field is 0. As you are moving for 1 meter, at 1 meter, the electric field will be E naught. At 2 meter, electric field will be 2 E naught. At 5 meter, the electric field will be 5 E naught. So at a meter, the electric field will be E naught A, and at 2a meter, it will be twice a E naught. Okay. Now you have to find the total electric flux. Answer. Here again, student, you have to find the electric flux again for all the faces which are perpendicular, the surface area whose surface area is perpendicular to the electric field. Whatever may be the electric field, it is varying, but it is along the x-axis. So this will give you the flux 0. Again, I'm repeating, those surface which are perpendicular to the electric field will not encounter any field lines, so flux for that faces will be 0. So which phase is going to encounter the electric field lines and which will count the electric field lines? Only this phase here, the hashed phase, one phase, and this is the phase number 2. Only these two phases will encounter the field lines, and that two phases will count. Here the direction is I cap, for which one? Area vector, and here it is minus I cap. Okay student, now we'll find the flux, and for rest phases, the 4 phases, the electric flux will be 0. Now here the phi, suppose this is the surface 1 and this is the surface 2. Here the phi net, it is phi 1 plus phi 2. Here the phi 1, E naught x I dot, it is a square minus I, very good, E naught x I for this one, and the direction it is, and area a square dot a square I cap. But remember, don't be in hurry and cancel out. Remember, for this phase, the value of x will be, since from origin this phase is placed at distance a, so it will encounter the electric field E naught A. But this phase will encounter the electric field since it is 2a away, so it will encounter the electric field 2x equals to 2a. Okay, so here I'm writing here the E naught A, I dot minus I, it will be the minus, and a square. Okay, a square plus, here the E naught x will be how much? For this phase, x is 2a, so it is 2a into a square. Here the I dot I 1. Now the net flux, student, it is here 2 E naught AQ minus E naught AQ. So the net flux is E naught AQ, and this is the answer. I hope, student, you understand very well. In the same way you can solve the questions of this such type. Okay, next question, student, for the practice. This question I'm giving you, student, it has been asked in IIT-1, but remember this question is very simple. By using your IQ you can solve this question easily. Again, you are having a cube. Okay, this is a cube. And you have to find the electric flux not by the side faces, but you have to find the electric flux due to this diagonal phase. Electric flux due to this diagonal phase. I hope you are getting by this diagonal phase. Again, the side of cube is A, electric field is E naught J cap. The electric field is in upward direction. The very simple question. Okay, E naught J cap, it is moving in upward direction, and you have to find out the electric flux by this phase only. How you will solve? Pause the video and try to solve. Okay, student, now the answer. First of all, find out the area. This side is A, no doubt, but this side is how much? It is root 2A. It is root 2A. So the area will be A into root 2A, and it is root 2 times A square. Okay. Now look at here carefully. This area vector, if you talk about this area, vector, it is perpendicular to the E. But here this diagonal is being tilted by what angle? Angle will be 45 degree. So this will tilt by 45 degree. Look at here. If this is the diagonal and this is the electric field, so this diagonal is tilt by how much angle? Those both are parallel. It is tilt by 45 degree, and this is the area vector. So flux, student, you can write here the E A cos theta we have been studied. Here the E is E naught J cap. Now you are not required to write the cap because we have been taken here the cos theta. So the E naught and A, it is how much? A is root 2 times A square, and cosine theta, that is the cos 45. So the flux is E naught root 2 A square times 1 by root 2. It is cancelled out, and the flux is E naught A square, and this is the answer, student. Okay. Now students, we will talk about the Gauss law. To study the Gauss law, student, we should have a concept of Gaussian surface. Okay, Gaussian surface. Gaussian surface. The name of this physicist was Carl Friedrich Gauss. He has been given this particular law. Gaussian surface has certain properties. One, it should be three-dimensional. Okay, it should be three-dimensional. Gaussian surface, you have to take symmetric. Remember, symmetric. Why symmetric? For simplicity. It would be easy for your calculation. Okay. And the third, which is most important, electric field must be considered. E must be considered on the surface of Gaussian surface. Okay, you have to study the electric field on the Gaussian surface. This is the very important. Okay, so this will be the, and Gaussian surface, the structure and the shape of Gaussian surface. What will be the Gaussian surface? You can take of any shape, three-dimensional, but the symmetric shape will give you the easy way to find the electric field. Remember, it will give you the easy way to find the electric field. Now, Gaussian surface, the if you will try to define the Gaussian surface, so Gaussian surface is a three-dimensional symmetric surface that encloses a charge. Suppose it is the charge, encloses a charge in such a way that you cannot taken out this charge without touching the Gaussian surface. It is like a chocolate placed inside a balloon. Okay, try to recall the birthday balloon and chocolate inside the balloon. This is like a chocolate placed inside a balloon. You cannot touch this chocolate without touching the skin of the balloon. So this is the Gaussian surface. Okay, this is the Gaussian surface, and this Gaussian surface will be considered as the symmetric for simplicity. Okay, for simple calculation. Now student, the statement of Gauss law. Okay, today we will study the statement, and from next class we will apply the application of Gauss law, how to prove this Gauss law, and what are the uses of this Gauss law, my dear student. And statement of this Gauss law, students, in such a way, the Gauss law, the statement is the total electric field lines encountered by this Gaussian surface, total electric field lines, remember total flux, actually I am telling, the total electric field lines encountered by this surface, Gaussian surface, must be equals the, that is the total flux, here the phi net, it is must be equals to 1 by epsilon naught times, okay, 1 by epsilon naught times the net charge, enclosed by this Gaussian surface. This is the Gauss law. In another word, you can explain this Gauss law as it is mentioned in your book. You can write the net flux, student, remember this is the another statement. Okay, the first statement, this one, now the another statement, this was the first statement. The second statement I am giving you, it is the surface integral, okay, surface integral of electric field. This is the electric field, and the surface integral, closed surface integral of electric field, the net flux will be equals the surface integral of electric field. This is also called the closed contour. So the surface integral of electric field in the net flux will be equals the surface integral of electric field, and this is also equals the 1 by epsilon naught times the enclosed charge. Which charge? This charge should be enclosed within the Gaussian surface. The charge which is out of the Gaussian surface will not consider here in Q enclosed. Okay, student. So this is the simple definition and the statement of Gauss law. In next class, student, we will prove this Gauss law. Thank you, student.